All right, so we're going to look at relative velocity, Giancoli 3.8. Um, so we've looked at relative speed in one dimension, and it's very similar in two dimensions, except we just must add and subtract velocities as vectors, just like we did with projectile motion. So each velocity is labeled first with the object and second with the frame of reference. Okay, so like for example, VWS is the velocity of the water in respect to the shore. VBS is the velocity of a boat in respect to the shore, and then VBW is the velocity of the boat in the water's frame of reference. Okay, so that's what some of the labeling is going to mean. Obviously, if you come up with your own way to label things, that would probably be best. So here's an example. So we have the three velocities. Okay, so you have the velocity of the boat in the water. Okay, it's a straight line velocity. You have the velocity of the water in relation to the shore, so that's kind of like the current, right? And then this is going to be what the boat does in relation to the shore. So this is what somebody standing on the shore sees the boat doing. So if you're on the boat, you feel like you're traveling straight. The water is going this direction in relation to the shore. So if you're in the shore, you're seeing the water traveling, and then you're going to watch the boat. Even though if you're on the boat, you're going this way. But in reality, you're going to be moving this way. It's going to be relative velocity, okay? And so then you can use trig functions to solve for these things, okay? So for example, 310 heading upstream, a boat's speed in still water is 1.85 meters per second if the boat is to travel north directly across the river whose westward current is 1.20 meters per second. At what angle must the boat head? So there's the diagram, and do this problem now.
All right, example 310, heading upstream, boat speed in still water is 1.85 meters per second if the boat is to travel north directly across the river, whose westward current has a speed of 1.20 meters per second. At what upstream angle must the boat head? So kind of took the image from the problem and put it up on the board. And again, this is the boat's speed in still water. Okay, this is the boat in direction of the water, and then this is the boat's this is the water's direction with the shore here in relation to the shore. So this is the boat to the shore, this is the water to the shore, and this is the boat to the water. Okay, so we're adding vectors together. Our goal is to get to a right angle so that we can use a trig. It says our VBW, right? So that's this is 1.85. And then we look at the water speed, which is 1.20. So at what angle do we have to travel to go straight across? Okay, and that's what we're looking for here. So that's what we're trying to find. To do that, we have a right triangle here, and we know the opposite, and we know the hypotenuse. So that's going to lead us to sine. So sine theta is opposite over hypotenuse. That's an 8. Our theta is going to be the inverse sine of 1.2 over 1.85. And we've done some of these, not tons, but inverse sine of 2o divided by 1.85. Make sure you're in degrees, and you get an angle of 40.4 degrees.
Example 311, heading across the river. The same boat now heads directly across the river. The current's still 1.20, and the boat in relation to the water is 1.85. And we want to know what velocity here the boat's traveling and in what direction. So we want to have the angle. And then if the river is 110 meters wide, so this is the width of the river, how far downstream, so how far down here, where the boat ended. And again, we will show that when we show the on the board. So do it now.
All right, example 311, heading across the river. Same boat that we had in a previous example. So going 1.85 meters per second, heads directly across the river whose current is still 1.20 meters per second. What is the velocity of the boat relative to the shore? So we're trying to find this, okay? Because we're going this way, the current's pulling us this way, so we're going to actually travel in this direction. And we want to know the magnitude direction of the boat. And then also, if the river is 110 meters long, we want to know how far from our straight across point we're going to end up, okay? And so that's going to be x. So we want to first solve for a. So let's do a. To solve for our magnitude of our velocity, it's Pythagorean theorem. This is a right angle. So I take vs squared equals 1.20 squared plus 1.85 squared. And then we'll work some magic there. 1.20 squared plus 1.85 squared. And then I take the square root of that. And I get 2.21 meters per second. All right, so now I have this. Now I want to find my angle. Again, I'm a tangent guy. I know all sides, so it doesn't matter which one you use, but it's opposite over adjacent. So theta is going to be the arctan of 1.2 over 1.85. So inverse tan of 1.2 divided by 1.85. Again, make sure you're in degrees. I get an angle of actually 33.0 degrees. That's what it rounds to. All right. So now that I know this, and I know this vector and what's heading, right? I can then use information for this. Now, remember when we did projectile motion, we separated x and y. We do the same thing here. So in our y, right, our distance is 110 meters, and our constant velocity is 1.85. So luckily, there's no acceleration going on here, so I can use simple velocity definition. Velocity is displacement over time. Okay, so my velocity is 1.85 in the vertical. My displacement is 110. Solve for t, okay? So t is equal to 110 over 1.85. You can check my algebra if you don't believe me. 110 divided by 1.85, and it's 59.5 seconds, all right? So that's our time to get across. Now remember, our time, we're heading in this direction totally, but our time in the x and time in the y are going to be the same, right? So if I know my velocity in the y is 1.20, I'm going to do it over here for space, or in the x, my velocity in the x is 1.20. It's also going to be distance over time, but now I know time. So my velocity is 1.20. My time is the same in the x as it is in the y, 59.5. Solve for distance. So my distance downstream from where I started, 1.2 times 59.5. Even though there's rounding, I'm at 71.4 meters.